Okay, we're going to study the units of measurement, and we will be referencing the metric system as well as the English system, just so we have something that we can compare to and understand since we are used to the English system. Measurement is defined as a quantity that has both a number and a unit. We don't just say that there's 5 or we have 20. We say we have 1 inch or 2.54 centimeters, 500 milliliters, or a gallon of something. These units come from standards of measurement. So when we measure, we use a measuring tool or apparatus, and we compare some dimension of an object to a standard. The standard is an exact quantity that people have agreed on to use for their comparisons and measurement. The first such system of measurement was called the metric system, and an improved version of the metric system was devised and is now called the International System, or the SI system. Why is the metric system easy? And notice I have that in quotes. It's easy to most people, but here in the States we don't use it from birth like everybody else does, so it is somewhat of a challenge for us. It's supposed to be easy because it's based on the number 10. We don't have to remember all these various equivalencies or standards of measurement. It's just powers of 10. It is used in most of the world. We are one of the only countries that does not use this for all measurements. Scientists and hospitals use it. It does create uniformity of measurement, which makes it easy to collaborate and communicate amongst each other because you don't have to sit there and think about units. It's the same for everybody. How do we state a measurement? In every measurement, there is a number, so that's the value you're getting from your apparatus, and it's followed by a unit from the measuring device. So that tells us how we measured it or what type of tool that we used. And I apologize, I am outside, so you will probably hear cars and things going by, just as there was one now. So once again, there is a number, and it's followed by a unit. So what are these units that we need? We have direct measurement, so they're obtained from a single tool or apparatus. The table has the quantity in the first column. The center column is the unit, so that's what we're going to use to label our numbers. And then the symbol, that's the abbreviation for those units. So if we're measuring length of an object, we want to use a meter, and its symbol is M. If we want to measure the mass of an object, its unit is gram with the symbol of G. When measuring the volume, we use liter and the symbol is L. And temperature, the accepted unit is Kelvin, and we do use that when we're talking about the gas laws, but it's not on the base power 10, so we use degrees Celsius. It's easier to use. Time, we use second. That by nature is not on a base power of 10. We use that, and that's based against the standard of the natural occurring motion of the Earth and the solar system. So that one we do have a lot of different variables and conversion factors to think about. Amount is mole. We're not too familiar with this number, but you guys all know what a dozen is. If we buy a dozen eggs, we're getting 12 eggs. So a mole represents the amount, and it has a specific number with it. So if we're talking about atoms, and we have 1 mole of atoms, we have 6.02 times 10 to the 23rd atoms. If we have a mole of eggs, we have 6.02 times 10 to the 23rd eggs. That is a lot of eggs. We also have derived measurements, meaning they come from more than one measurement or they are calculated. So once again, the data table is showing our quantity, the unit, and then the symbol for that unit. Area is measured by square meters, or m with the exponent of 2. You can also use centimeters for a smaller object, so that would be cm with the exponent of 2. Volume is cubic meters, or m with the exponent 3. density is something we use a lot, is kilograms per cubic meter. So it's kg divided by m to the third, or we can have g divided by centimeters to the third, so cm cubed. And we could also have grams per milliliters or kilograms per liters. That one has a lot of different ways we can express it depending on how we obtain the measurements. Pressure, we use pascals. Notice that symbol is PA, but it represents kilograms per meter second squared. So that's kg divided by ms squared. We also have energy, frequency, and electric charge, and those are things we'll deal with when we talk about the atom. Oh, sorry, I think we mixed the prefixes. Let's rewind. We need prefixes before we can convert. Our prefixes represent our powers of 10, so they are written before the base unit to let us know how big or how small our measurement was. So the prefix is our first column, its symbol is in the second column, and then the meaning, how we would relate to that to a power of 10, and then how we would see it as a decimal system. So giga is a capital G representing billion or 10 to the 9th. Mega is a capital M representing million or 10 to the 6th. Kilo is a lowercase k representing 1,000 or 10 to the 3rd. Hecto is H meaning 100 or 10 to the 2nd. And deca is DA meaning 10 to the 1st, which is kind of silly. It's just 10. And then those numbers are all bigger than our base. So if we're not just weighing a gram, and we see one of those symbols in front of it, that means we are bigger than a gram. Our base unit is 10 to the 0, so that's the same thing as saying 1, even more silly to write. Now let's go to our smaller items. We have deci, which is a D, which means 1/10, or 1 over 10, and notice that says 10 to the negative 1. When you have a negative exponent, that means you have a fraction, 1 over 10. Centi is C, meaning hundredth, so 10 to the negative 2, or 1 over 100. Milli is M, meaning thousandth, 1 divided by 1,000, or 10 to the negative third. Micro, ooh, he's a silly guy. He looks like a backwards Y or a U with a leading tail, and that's 1 millionth, and that is 10 to the minus 6th. And a lot of things in the bio field has gone to microbiology, meaning we're looking at teeny items within organisms. And then we have nano, which is a billionth. Its symbol is N, so we have 10 to the negative 9. Notice in the big numbers, the power is equal to the amount of zeros that you see after the 1. But in these smaller powers, the negative powers, you have 1 less 0 after the decimal place. So don't get confused and think the numbers tell you how many zeros there are. So that would be our prefixes for the metric system. But we often need to convert, so let's move to conversions. Conversions mean that we need to change units. So we have a conversion factor or equivalency. So that's the ratio of the equivalent measurements. So an example is for 1 meter, there are 100 centimeters, and for 1 kilometer, there's 1,000 meters. So we can express that as a fraction, or we can use the ratio 1:100 for meters to centimeters. But we prefer the fractions. How do we actually convert units? We use dimensional analysis or factor label. Not all objects that are measured are in the units that we need. So factor label or dimensional analysis is a mathematical way to convert from the units you have to the units you need or want. In order to eliminate the unwanted units, you design a ladder type setup or picket fence setup of equalities that cancel out, so you get rid of the units you don't want and are left with the one you do desire. It is a way to analyze and solve problems, and it does use units or dimensions of measurement. You can't just have numbers, you have to have units here. So let's look at our first example if we want to convert 17 inches to feet. So starting with something we know. We have 17 inches. There are 12 inches in 1 foot. So notice the inches is in the underneath feet so that they cancel out, or when you divide by like variables, it becomes 1. So if you had x divided by x, that's the same as 1. Here we have inches divided by inches, so that makes it a 1. So mathematically, we have 17 divided by 12 gives us 1.4 feet. Now let's look at a metric example. If we have 35 centimeters, we want to go to meters. So for every 1 meter, there's 100 centimeters. Centimeters needs to go on the bottom, so they cancel out, and our answer becomes 0.35 meters. Now we're going to go from a large item to a small item. So we have 6.4 kilometers, and we want to get to meters. So there are 1,000 meters to every 1 kilometer, and that gives us 6,400 meters. Multi-conversions, I always use base as our middle or our baseline, so it's hard to remember how many centimeters in a kilometer. So if you start from kilometer, go to base, and then move to centimeters, it does make life a little easier. So we have 6.4 kilometers here, and there are 1,000 meters in a kilometer, 100 centimeters in a meter, and so we get 640,000 centimeters. Okay, now let's look at a standard conversion that we would do. We would have maybe 15 inches, and we want to see how many yards that is. So if you have 15 inches, you have 1 foot, has 12 inches in it, and 1 yard is 3 feet. So you have 15 inches, you divide by 12, and then you also divide by 3 to give you 0.42 yards. So notice in this case we're dividing. Anything that is down low, you need to divide. Anything that is up high gets multiplied. So our tops are 1s, and when we multiply by 1, it doesn't change our number. So basically we're doing 15 divided by 12 divided by 3, and we can ignore those 1s. So this concludes the metric system, SI system, units, prefixes, and how to convert in between those different units. There is a practice sheet that contains examples and guides on how to do this. The graphic organizers are present within those practice sheets.